In this video, we will introduce real-time safe and smooth visual servoing for robot manipulators via reinforcement learning. The two pictures above show the environment settings of our two cases this time. The picture on the left is reaching task environment, which includes a robot, a RealSense camera, and obstacles. The picture on the right is dynamic target tracking task environment, which includes a robot, a target point, obstacles, and a mobile carrier. We established a digital twin environment for training based on these two scenarios, and finally placed the training results in a real scenario for verification. The three videos shown here are the results of reaching task trained by three algorithms. We set the initial pose of the robot and select the endpoint, then randomly place the obstacle position, obtain the obstacle position through the RGBD camera, and then obtain the position of the obstacle relative to the robot through coordinate transformation, and use the feedback position as parameters are input into the state space to control the obstacle avoidance planning of the robot. The picture in the lower right corner shows the real-time error of the robot end effector from the target point during the planning process of the three algorithms. The video here is the result of dynamic target tracking task. We obtain the obstacle position and the real-time position of the target point through the camera and input them into the state space as parameters. The first half of this video is a tracking situation where the target point moves to the right, and the second half is a tracking situation where the target point moves to the left. At the same time, the picture on the right also shows the real-time error during the tracking process. It can be seen that the tracking error shown in the figure fluctuates greatly. The main reason is that collisions must be avoided during the tracking process. The above two cases are the results after adding low-pass Butterworth filter and velocity blending during the training process. Their main purpose is to reduce the randomness of the reinforcement learning output results that cause the mechanical arm to shake violently. Judging from the movement process and the drawing of the end path in the above video, the robotic arm has almost no jitter during movement. In this paper, we added low-pass Butterworth filter and velocity blending for training. Judging from the convergence of the reward function, adding the two modules did not have much impact on the training efficiency and effect of the algorithm. On the contrary, in the training results of some algorithms, adding modules performs better. The success rate of reinforcement learning is not 100% successful. From the success rate in the figure above, we can see that there are several sets of comparative experiments with lower success rates. At the same time, when we verified it in the real scene, there were also multiple collisions, and the target point cannot be reached within the specified step size. However, according to statistics, the success rate of adding filtering and velocity blending is still at a high level. On the contrary, simply using the algorithm for training has a lower success rate, and thus confirms the superiority of our method. This is a comparison chart of the computing time for completing a single round of the task. We recorded the computing time of 100 successful episodes and used a bar chart to represent the time interval. The red star represents the average time. It can be seen that the computing time increases slightly after adding the module, but the overall impact is not significant. The above is an introduction to this paper. Thank you for watching.